What's up everyone, welcome back. Patrick here, and moving on to the next concept in the course, we're now going to talk about the intermediate value theorem. And so what I'm going to do in this overview video is first go over the theorem. Notice it's already written out here, but I'm going to break it down a little bit more, show you visually how it works in general, and then I'll go over an example at the end of this video, and then a couple of other examples in the next few videos where we have to apply this theorem, just so you can get an idea of first how it works and then how it is applied. So let's read the theorem. We're told, given that f of x is continuous on the interval a and b, where x is between a and b, and f of a does not equal f of b, if n, which is just some kind of number, is in between f of a and f of b, then there exists a number c on the interval where c is between a and b, where f of c is equal to n. So I know reading that sounds a little bit confusing, but if we break it down, it's actually not too bad. So let's go through each sentence one by one. So we're told f of x is continuous on the interval between a and b, where x is greater than a but less than b. So let's pick an x value here of a. Let's pick an x value here of b. And we're told that this function is continuous between these two x values. So this function can maybe be like a line, or maybe it could be, let's say, like a parabola, or it could be a wave. It could be anything, right? It could be some kind of weird function maybe like that, right? Point is, it's always going to be continuous on that interval between a and b. And then we're also told that f of a does not equal f of b. And notice, what is f of a? F of a is basically the y value when x is equal to a. And then same thing with f of b. It's basically the y value of this function when x is equal to b. And we're told that f of a, those two y values are not equal. So let's say that f of a is over here. And so this function is going to have this coordinate. This coordinate here is going to be a, the x value, and then the y value, f of a. And then let's say, remember, f of a and f of b cannot equal, so let's say f of b is larger than f of a. So let's say it's up here. And so that coordinate is going to be up there. So let's say this coordinate is b and f of b. Now, f of b doesn't necessarily have to be greater than a. It could also be less than f of a, right? So we could have put f of b down here as well. But just for now, for this example, for this explanation, I'm going to assume f of b is greater than f of a. The most important thing is that they're not equal. Right? We got this y value, and then we got that y value, two different y values. Okay, so we're up to here, and then we're told if n is in between f of a and f of b. So the number n is in between f of a and f of b. So let's say n is over here, right? And so let's draw a dotted line for n, right? So throughout this horizontal line here, that's always going to have a y value of n. So n is between f of a and f of b, which we just drew. What that means is that there exists a number c on the interval where c is between a and b. So a and b, so there's going to be some kind of number c where f of c is going to equal n. Okay, meaning that this function has to cross this horizontal line within that interval if it's continuous. Notice that there's no way to get from this point to this point on this interval without crossing this line. So let's say it looks something like that. Well, let's erase this c. Notice that over here, for this n value, there exists a number c, where f of c is equal to n. Basically, they're saying that there's some kind of coordinate c and n somewhere here, right? It's going to cross somewhere. And sometimes it could even cross multiple times. So this function can easily maybe even look like this. So there could be multiple c values in between a and b that are going to have that y value of n, right? That's basically what the theorem is saying, is that there's going to be some kind of number in between a and b, some kind of number c, where f of c is going to equal n. It's going to equal that y value of n, because from here to this point, if the function is continuous, it has to cross that horizontal line at some point within that interval. That's basically what this theorem is saying. And notice that if I redrew another scenario, let's say f of a is up here, and then f of b is down here. Let's say in this case, f of b is lower than f of a. As I mentioned, that could happen as well. They just can't equal. And there exists a number, n, in between them. The n can be anywhere. I'm putting it sort of closer to the middle just to visually show you, but n can be up here, n could be down here. And if this function is continuous, right, it could even maybe like rise up, but if it's continuous, it has to come back down to this coordinate, b and f of b. And so it has to cross this horizontal line, this y value of n. And what they're saying is that there's going to exist some kind of number c in between a and b, where f of c is going to equal n. So whether it crosses here, maybe it'll cross here, maybe it'll cross multiple times, and there will be multiple c values. Either way, there has to be one kind of c value where f of c, between a and b, where f of c is equal to n, if n is between f of a and f of b. Right? Hopefully that kind of makes sense. Basically what this theorem is used for is to show that certain functions can take a certain value, a certain y value, within a certain interval. So if we do an example, we're asked to show that there exists a number c where c is between 10 and 15, such that f of c is equal to 500 if f of x is equal to x squared plus 20x. And to solve this kind of question, we're going to use the intermediate value theorem. So if I draw this out, notice the interval we're working with for c is between 10 and 15. So I'm going to draw 10 and 15 over here. Also notice that x squared plus 20x is continuous for all x values. But more importantly, it's continuous within this interval. It's continuous for XCR. Since it's continuous for XCR, it's continuous between the interval 10 and 15. And what we can actually do is find out what is f of 10 and what is f of 15. So notice if we plug in 10 for this function, we'll have 10 squared plus 20 times 10, which would give us 300. And if we plug in 15, we'll have 15 squared, which is 225, plus 20 times 15, which is 300. So we'll have 225 plus 300, which gives us 525. And so if we label that, f of 10 is 300. So let's label that down here. We got that coordinate for this function. And then we're told also that f of 15, or we figured out that f of 15 is going to be 525. So let's say 525 is up here. This is not necessarily to scale, but just kind of drawing a graph here to show you visually what's happening. So 15 and 525 is a coordinate on this function. as well, up there. And so by the intermediate value theorem, because this function is continuous between these 2 points, there has to be a number c in between 10 and 15 where this function is going to equal 500, because notice that 500 is between 300 and 525. So no matter how this function looks, we know it's continuous from here to here. It's just a regular parabola. But let's say it was an even more complex function where we don't know how it looks. Doesn't matter how it looks. All we know is that at some point, it's got to cross that horizontal line. And so let's say that it, how would this parabola look like? Yeah, it's coming from down here. But anyway, let's just say it looks like this. Notice that it has to cross that horizontal line at some point. And notice that when it does cross that horizontal line, when it does have that y value of 500, the x value, right, the corresponding x value for that point that has a y value of 500 is going to be between 10 and 15. Right? So we showed with the intermediate value theorem that there exists a number c between 10 and 15 such that f of c is equal to 500. And if you were to put this in a sentence, what you can do is you can actually apply this to this sentence. So you could erase certain things. So we can say, given f of x, and we can write out the function here, equals x squared plus 20x, is continuous on the interval where x is between a and b, but instead of writing a and b, let's write 10 and 15. And f of a does not equal f of b. We know f of a is 300, right? So instead of a, we have a 10 here. F of 10 is 300. F of 15 is 525. They don't equal. Those two y values don't equal. If n, the n value we're looking at is this 500. So we would put 500 here. If 500 is in between f of a, which is f of 10, which is 300, and f of 15, which is 525. So notice that 500 is in between f of 10 and f of 15, in between 300 and 525. Then by the intermediate value theorem, there exists a number c on the interval between 10 and 15, where f of c is going to equal 500. Right, so you could draw this sort of diagram and then you can put it in a sentence like I just did. Instead of writing the general stuff in the theorem, you could just sub in whatever you are, what you're working with. And that's what we're going to be doing in the next few examples. I'm going to have this theorem written out, and what I'm going to do is I'm going to apply the parameters in the question that were given to the theorem. So I'll kind of be like erasing things and just subbing in, and then once you have that sentence written out, then it is correct because you're using a theorem to show the result that you're looking for.